I want to try to illustrate to you a little bit of how the chain rule works graphically. What I have is two functions. The first is this parabola f of x. And the second is going to be this function h of x that's a composition. It's f of 2x. And what taking f of 2x does is it horizontally compresses the function f of x. So this sort of wider bottom parabola gets compressed down into this narrower parabola f of 2x. And indeed, I might note here that this f of 2x here, that really what you have going on is some inside function that I could call g, and my g is just equal to the function 2x. So in other words, what you have is a composition. F of g is going to be this particular function, h of x. So before we look at what happens graphically, let's just compute this out algebraically. That is, if I want to figure out what the derivative of h is, so if I want to figure out what h prime of x is, we use the chain rule. And the chain rule says first, derivative of the outside, which is going to be the function f, so it's going to be the f prime, at the inside, so f prime at the value of 2x, derivative of the outside at the inside, and then I need to do that final point where I multiply by the derivative of the inside. But the inside function here is just going to be this 2x. So I'm multiplying by the derivative of 2x. The derivative of 2x is just 2. So what I'm multiplying by is just 2. So in other words, what we're saying here is that the derivative of h is just like the derivative of f, but there's this sort of horizontal compression factor, the 2x at the inside, and then there's also another 2 that's multiplied on the outside, which is kind of interesting. So let's see how this works. First of all, I want to focus on where my f and my g have horizontal tangent lines, where they have zero derivatives. So we can notice those 2 points. The one here is occurring at a half. That's when this h of x is going to have the derivative of 0, a horizontal tangent line. But for the f, it doesn't occur over here at the value of 1. That's when it has a derivative of 0, or a horizontal tangent line. So let's see if that actually makes sense. I'm going to plug in some specific values here. I want to look at h prime of 0.5 here. And what that tells me is I want to look at f prime of twice a half. So in other words, f prime of 1 multiplied by the value of 2. But f prime of 1 we just said was equal to 0, and so that's equal to 0. So my formula seems to be pretty good so far. It says the derivative of a half is, just by chain rule, the f prime of 1 times 2, so I get 0, and everything works out. I get exactly what I anticipated. All right, that was lovely. Let's try just another point to see whether the formula still makes sense. Now, notice that there's these two pieces to this formula, because it's the product of two things. The first part is saying the derivative of h is just like the derivative of f, but not at the same point. It slides where the point occurs. It goes from the derivative at a half is, well, you look to the derivative at 1, and then you multiply it by 2. So here, to figure out the derivative down here of the h, what I did was I looked at the derivative of the f at twice at 1, and then I multiplied by 2. And in this example, the multiplication by 2 doesn't do much, because it's just taking a 0 and multiplying it by 2, I get another 0. But let me look at a different point. Let me look at what happens at 1. So I've got put in my 2 different tangent lines. And then what we say is that if I want to look at this tangent line, what I do is I look over here at f prime at twice the point. So instead of looking at 1, I come over here at f and I look at the value of 2. What is f prime at 2? But if you'll notice that the slopes have also changed. This is a little flatter and that's a little steeper. And that's because of this multiplication by 2. So when I'm figuring out the derivative of h, I both look to the derivative of f at twice the point in this case, going over to 2x and not x, but I also multiply its slope by 2. So as we come here, you get this multiplication by 2, and this slope is steeper by a factor of 2 than that one is. Now, this is admittedly a relatively straightforward example only because the inside function, the g of x, is equal to 2x, which is a relatively simple function. But if I had a really complicated f and a really complicated g, the same idea sort of works, which is that to figure out the derivative of a composition, you look to the derivative of the outside function evaluated at wherever the inside function is going to take you, but then you multiply by this sort of modulating factor, the 2 in this case, or generically the derivative of the inside. And so you have this product of these two different things.